Welcome to today's deep dive.
Thanks for having me.
Yeah, so today we are tackling a question for you that seems, I don't know, almost contradictory at first glance.
It really does.
Right. It's this idea of how does looking at the absolute smallest microscopic, like subcellular pieces of our planet, how does that actually help us solve the largest, most existential macro scale challenges of our future?
It is the ultimate exercise in scale. I mean, traditionally in the geosciences, we're accustomed to looking at massive global systems.
Sure, like tectonic plates.
Exactly. Tectonic plates, atmospheric currents, planetary orbits, looking at the big picture to find answers to our biggest problems.
Right.
But the paradigm is shifting. Today, the most crucial answers are found by looking inward and downward into the subatomic building blocks of the Earth.
Okay, let's unpack this. Our mission for this deep dive with you today is to explore those absolute cutting-edge frontiers.
The bleeding edge.
Yeah. We are going to connect the dots between the discovery of microscopic new minerals that could completely revolutionize the green energy sector,
Huge implications there.
all the way to how leading universities are literally overhauling how they train the next generation of Earth scientists to, well, save the world.
That's the goal.
So to do this, we're pulling from a really specific stack of sources.
That's a great stack.
First, we have a fascinating news report from China Daily. It's about a newly approved mineral called Jinxiuite.
A very recent discovery.
Right. Then we're pairing that with an Earth.com article detailing how the sub-100 micron crystal called Ehrigite is just shaking up the entire global mining industry.
Forcing them to rewrite their models.
Completely. And to ground all this high-level tech, we have the incredibly dense, story-filled spring 2026 Tectonic newsletter.
From Virginia Tech's Department of Geosciences.
Exactly. It's a deep look at the human capital, the researchers, the funding, the people actually driving these scientific leaps.
It's a really powerful combination of texts. You've got the raw discovery of new materials in the field, the computational application of those materials in the lab, and then the educational infrastructure required to sustain all this innovation over decades.
Because it doesn't happen in a vacuum.
No, it doesn't. And if there's a unifying theme for you today, it's that micro-scale clues lead to macro-scale survival.
I love that because, I think for a lot of people outside the field, when you say geology, they picture,
A flannel shirt and a rock hammer.
yes, someone just hitting a rock outcrop. But today's dive is going to prove that modern geoscience is fundamentally a high-tech discipline.
Highly technical.
We're talking applied climate solutions, astrobiology, multi-million-dollar green energy mapping.
The rock hammer is still there, sure.
Yeah.
But it's been augmented by atomic resolution microscopes and supercomputer clusters.
And there's no better place to see this shift than at the frontier of mineral discovery.
Absolutely.
So let's start there. This China Daily report.
Jinxiuite's discovery.
Right. Back in June, researchers at the Chinese Academy of Geological Sciences found a brand new mineral,
In the Longhua nickel-cobalt deposit.
which is in the Jinxiuite Autonomous County in Guangxi.
Hence the name Jinxiuite.
Exactly. And it was officially approved by the International Mineralogical Association. But the big deal isn't just that it's new.
No, it's what it's made of.
Right.
The elemental makeup here is what makes this a geopolitical focal point.
Okay, break that down for us.
So Tang Hejun, the senior engineer who led the discovery, highlighted that this mineral is a composite. It contains nickel, cobalt, and bismuth.
Okay.
That is a highly strategic combination of elements.
Because if you look at the broader context, nickel and cobalt, those are non-negotiable for modern infrastructure.
You cannot scale a green energy grid without them.
Or make high-capacity batteries.
Or sustain an aerospace program. They provide the thermal stability, the high temperature resistance, the corrosion resistance.
Everything modern tech needs to not melt down under stress.
Exactly. And this hits right at a critical vulnerability for China.
Which Tang Hejun points out.
He does. China historically has very limited domestic resources of these specific metals. They rely heavily on imports, especially for cobalt.
So when your entire manufacturing sector is bottlenecked by importing one element,
Finding a native mineral deposit that naturally concentrates these metals, that is a massive strategic victory. It alters their domestic supply chain calculus completely.
But Tang also makes a crucial distinction about the operational side, right? Like, finding the deposit is one thing.
Right. Just because it's there doesn't mean you can use it.
Exactly.
Yeah.
The economic viability hinges on extraction.
The ease of extracting those metals from the specific crystalline structure of Jinxiuite dictates the recovery rate.
So if the chemical bonds are just too strong?
If they're too energy intensive to break at an industrial scale, the deposit is theoretically valuable but practically useless.
Wow.
It's the defining hurdle of modern metallurgy. You have to weigh the energy cost of the chemical reagents, the thermal processing needed to liberate the cobalt from the bismuth and nickel.
It's a massive equation.
It is. But Yanjie Yang, he's the director of the Academy's Deep Mineral Exploration Division. He takes it a step further.
Yeah, his quote was fascinating.
He says discovering new minerals like this acts as a natural blueprint for materials science.
A natural blueprint, that's like biomimicry, but for geology.
Exactly. Nature has spent billions of years experimenting in these subterranean, high-pressure, high-temperature laboratories.
Just mixing chemicals in the dark.
Right. So when we find a novel mineral structure, we're uncovering a chemical recipe that we didn't even know was stable.
And that can inspire material scientists to synthesize entirely new artificial materials.
With bespoke properties. Plus, Yan views these minerals as geological hard drives.
Records of the universe's history.
By analyzing how Jinxiuite associates with surrounding minerals, its paragenesis, geochemists can reverse engineer the geological history of the deposit.
Which gives you the tectonic history of the whole region. It's deep-time forensic science.
It really is.
And that concept of microscopic minerals acting as these massive geological signposts that leads us perfectly into the Earth.com piece.
The Ehrigite story.
Right. Hiding in plain sight in British Columbia.
At the Good Hope mine, which is already a fascinating geological setting, complex skarn formations.
But the Ehrigite discovery is just a testament to sheer persistence.
Oh, without a doubt.
The formula is B8T3, a bismuth telluride. But the chemistry isn't what blew my mind. It was the physical scale.
Sub-100 micron grains.
Less than 1/10 the width of a human hair. The article said it was a speck so small that a grain of sand could drown it in shadow.
It's incredibly evocative, and it took Associate Professor Cristiana Ciabani and Professor Nigel Cook over a decade of detective work to formally document this.
A decade for a speck.
Because the International Mineralogical Association's vetting process is brutal.
Right. They use independent reviewers from like a dozen countries.
To put it in perspective for you, out of all the crystals analyzed globally every year, only about 100 new species get approved.
Wow.
As of May 2025, the total validated list is just 6,145 entries.
That's an exclusive club. And Ehrigite got in because of what it concentrates, right? Tellurium.
Tellurium, which is on the 2022 U.S. Critical Minerals list.
And it's rare.
Incredibly rare.
Yeah.
We're talking 1 part per billion in the Earth's continental crust.
1 part per billion. So finding any mineral phase that naturally aggregates it.
Even on a sub-100 micron scale, it triggers massive industrial interest.
Because we need tellurium for green energy.
Vital for cadmium telluride thin film solar panels and for advanced thermoelectrics.
Let's explain thermoelectrics really quick. That's turning waste heat into electricity, right?
Exactly. Converting temperature differentials directly into electrical voltage.
Which is huge for energy efficiency.
Massive.
Yeah.
If you have an industrial smelting plant or a data center just pumping out waste heat, pure bismuth telluride modules can harvest that.
And feed it back into the grid.
Yes. They've hit over 6% conversion efficiency at like 482 degrees Fahrenheit. Every megawatt you recover reduces fossil fuel demand.
So identifying a primary tellurium concentrator like Ehrigite saves millions in exploration, but how do you even physically analyze something that small?
Especially when it's embedded in dense rock. You can't use standard optical or even standard scanning electron microscopes.
So what did Ciabanu's team use?
An atomic resolution transmission electron microscope with aberration correction. But the real game changer was a computational technique. Tachographic reconstruction.
Okay, here's where it gets really interesting. Because tachography isn't just taking a highly magnified picture.
No, it's not a single image at all. It's a computational method.
Because physical lenses have limits, right?
Even magnetic lenses and electron microscopes have aberrations. Tachography bypasses that. The microscope records thousands of overlapping diffraction patterns as the beam scans the sample.
Okay.
Then massive algorithms invert that scattering data, stitching it together to reconstruct the electron wave. The result is sub-Angstrom clarity.
Sub-Angstrom. So they're seeing features smaller than a single nanometer.
They are visualizing the atomic lattice itself. And what they saw was bismuth triplets alternating with tellurium layers,
A completely new structural pattern.
which holds more bismuth than classic bismuth telluride, so it might have unique electronic pathways for next-gen alloys.
And right now, we mostly get tellurium as a byproduct of copper refining, right?
The vast majority, yes.
So finding primary sources maps out a whole new supply chain, which brings us to geometallurgy.
Future of mining.
Exactly. Blending petrography, the detailed description of rocks with metallurgy.
To forecast exactly how ore will behave in the processing mill.
Before you even dig it up.
Right. And Ehrigite is named after Dr. Kathy Ehrig, who basically pioneered this shift.
The article mentions her work at BHP's Olympic Dam.
She built these comprehensive geometallurgical models. She wasn't just looking at copper grades. She analyzed alteration halos, trace elements,
To predict the exact grinding energy needed.
and recovery rates.
Yeah.
And those models cut processing costs by 15%.
15% at a massive mining scale is astronomical.
Huge financial and environmental savings. Grinding rock is one of the most energy-intensive processes on Earth.
So optimizing that saves money and reduces toxic tailings. And now, Siobanu and Cook are pushing this even further with machine learning.
They got an $894,000 Australian Research Council grant.
To ingest all this chemical assay data into AI clusters.
Textural scans, thermodynamic phase diagrams, the AI outputs probability maps for these high-grade microtellurides.
They're predicting how processing-friendly the rock is before a drill ever hits the ground.
Total paradigm shift. A single speck of Ehrigite tells the plant manager how millions of tons of surrounding rock will behave.
Years before the plant is even built. That is wild.
It really is.
Okay, let's pivot to the Virginia Tech newsletter, because we have another new mineral named after a brilliant scientist, Nancy Reshape,
Discovered in the Tsumeb district of Namibia.
alongside studite. But this discovery was a total accident, wasn't it?
Pure serendipity. They were picking out statite crystals for a high-pressure lab study. Statite is usually greenish-yellow.
But they noticed these honey-colored outliers.
Right, so they ran a single crystal X-ray diffraction, and the iron-oxygen octahedron of this honey-colored crystal was smaller.
Which confirmed it was a novel phase.
Named after VT Professor Nancy Ross. Meansy is the symbol.
And scientifically this matters because it's a germanate, germanium plus oxygen.
Exactly. Germanium sits right below silicon on the periodic table. It can substitute into silicate structures.
But germanites behave differently under pressure.
Drastically differently. The newsletter gives a great example. If you take magnesium silicate olivine, a very common mantle rock, and squeeze it, it turns into a denser spinal structure.
But that takes, what, 14 gigapascals of pressure?
14 GPa, that's roughly 138,000 atmospheres.
That's insane.
You'd need a diamond anvil cell. It's incredibly hard to study in a lab. But if you swap the silicon for germanium,
The phase transition happens at just 1.5 GPa.
about 15,000 atmospheres. Still intense, but experimentally. Much, much easier to access.
Which lets researchers study perovskite structures with way higher precision.
And perovskites are the holy grail of material science right now.
Solar panels, hard drives.
LEDs, superconductors.
So this microscopic, honey-colored crystal is a proxy for deep Earth geophysics and next-gen electronics.
It connects everything.
It does. But, finding these microscopic solutions is just half the battle.
Right, because we have massive macro-scale consequences to deal with.
Namely, carbon.
The biggest geological challenge we face.
The VT newsletter points out a staggering stat. In 2025, the energy and manufacturing sectors produced over 38 billion tons of CO2.
38 billion. And yes, we use some of it, carbonated drinks, refrigerants.
But that's a drop in the bucket. We have to sequester the rest permanently.
Which is why Virginia Tech launched the Carbon Co-Lab.
Led by Dr. Ryan Polya. This isn't just one academic department, right?
No, it's massive, cross-disciplinary. Geosciences, mining engineering, chemical engineering, sustainable biomaterials.
Looking for real-world, scalable decarbonization. And they have serious funding. A $9 million DOE grant.
Plus $2.6 million from Titan America's Roanoke Cement Company.
They're using the cement plants surrounding geology as a test site, but the financial barrier for this stuff is huge.
It is a commercial-scale geological carbon storage project. It costs $250 to $300 million just to get operational.
Just for the permits, the environmental reviews, the drilling.
It's why industries hesitate. Carbon Co-Lab is trying to find affordable alternatives.
Like injecting CO2 into deep saline aquifers in Florida or using mafic mine waste.
Mafic rocks are rich in magnesium and iron. Expose them to CO2, they chemically react and form solid carbonate minerals.
Locking the carbon away as a solid. But to do that safely on a massive scale, you need to understand rock mechanics.
Exactly. You need the EM's lab, earth mechanics, and physics for energy sustainability.
Run by Dr. Mateo Acosta.
He joined VT in winter 2025 from Caltech, originally from Ecuador.
Which he points out has massive geothermal potential.
Right. And he studies how microscopic pore spaces and microfractures dictate rock strength.
Because if we're injecting billions of tons of fluid into the subsurface,
the biggest risk is altering the subsurface stress state,
inducing seismicity,
triggering earthquakes on pre-existing faults, or breaking the cap rock seal so the fluid leaks.
So Dr. Acosta's lab is simulating these extreme pressures,
recreating kilometer-scale depth conditions on large rock samples right in the lab, bridging that gap between micrometer processes and macro-scale fault behavior.
Building a predictive model the industry can actually trust.
And that desire for industry realism is shared by another new faculty member, Dr. Sam Haynes.
He joined in winter 2024, and he came straight from the industry, right?
The oil patch. He worked at Chevron, the Danish offshore technology center.
His research is on brittle fault rocks, dating fault gouges in the Himalayas and the Pyrenees to understand fault movement.
And he understands the oil and gas infrastructure intimately, how to retrofit depleted oil fields into carbon storage facilities.
He's actually teaching a new cross-disciplinary course on this with the depth of science, technology, and society.
Analyzing hydrocarbon systems holistically.
Yeah.
The geology, but also the social and economic impacts above ground.
And his advice to students entering this transitioning job market is just so grounded.
Be patient. Be flexible.
He tells them to get any job they can, even if it's not perfect, because it's easier to get the next one once you're employed.
It's vital realism for academia. And flexibility is key, because to engineer the future, we have to decode the past.
Which brings us to Dr. Julia Cisneros, decoding deep time.
She runs the Bedform Dynamics Research Group,
studying dunes and rivers. But she's using some intense tech. LiDAR, acoustic Doppler systems, subsurface echo sounders.
She maps the 3D velocity field of water flowing over sediment to quantify how bedforms initiate and migrate.
Why does that matter for the future, though?
Because sediment movement teaches us landscape evolution. How natural environments, rivers, coasts will respond to changing land use and climate change today.
It's the physical memory of the Earth.
While Dr. Pedro Menares is reading the biological memory.
Computational paleontology.
He joined in spring 2025. He's looking at macroevolutionary questions. Why do species go extinct? Or why do they thrive under stress?
He's using massive data sets, and he's challenging the whole status quo on mass extinctions.
The traditional view was fast extinction, protracted recovery.
But his data says the opposite for some events.
Longer extinction, faster recovery.
Which rewrites the fossil record. But again, to bring it back to the listener, why does dinosaur-era extinction data matter to us right now?
Because it's our only empirical baseline for survival. Menares emphasizes that fine-tuning our deep time data directly influences modern conservation biology.
We're in a biodiversity crisis now.
So understanding which ecological traits survived past extinctions provides the framework for triaging E-systems today.
That is so powerful, and his path to get there wasn't linear either. Pre-med, marine biology, now computational data.
Just like Dr. Floyd Nichols.
Right, astrobiology, moving from deep time to deep space.
Nichols studies lipid biomarkers.
Fatty cell walls that resist chemical degradation.
Exactly. He extracts them from extreme environments on Earth to trace the metabolic pathways of ancient bacteria.
He goes to hypersaline lakes, the Atacama Desert in Chile.
Which is the perfect terrestrial analog for Mars.
Yeah.
The desiccation, the UV radiation in the Atacama mirrors Jezero and Gale craters.
Where the NASA rovers are right now.
His work directly informs how we calibrate instruments to search for extraterrestrial life.
And he also started as a pre-med biology major, but he started hosting planetarium shows, got hooked on space, and a mentor guided him to astrobiology.
Mentorship is crucial, as is work-life balance, which he advocates heavily for.
Right. The newsletter mentions his lunar photography, playing chess, and his white mushroom risotto.
Biogeochemist who appreciates a good risotto.
You gotta love it. But that human element is the perfect pivot. Because none of this, the 14 GPA pressure cells, the machine learning, the Mars rovers, none of it exists without training brilliant minds.
The educational infrastructure is the foundation of it all.
How do you even teach a student to conceptualize a 100-micron telluride crystal?
With highly innovative teaching, like Dr. Laura Neeser's work.
The shape table.
Instead of just lecturing on seismic waves, She brings a portable, motorized shake table into the classroom.
To physically show why buildings of different heights suffer different earthquake damage based on frequency.
And she proves it works with pre- and post-assessments. Interactive learning is quantifiably better.
She also created that open-source textbook,
which won a CHEV Impact Award.
It's accessible, screen reader compatible, and totally free, removing the financial barrier. It's even being used in Cambodia.
Democratizing science. And Virginia Tech is modernizing the physical spaces, too.
The new undergraduate science lab building, floor-to-ceiling whiteboards, fossil unwrapping parties,
And the Museum of Geosciences Omniglobe,
which has reached 56,000 visitors.
showing 3D visualizations of tectonic plates and hurricane paths, though they are currently fundraising to repair it.
But the impact is undeniable. Seeing that stuff is what sparks a STEM career.
But the ultimate tool is field experience.
The Switzerland Study Abroad program, celebrating its 10th anniversary,
Based at the Steger Center, Villa Moderni.
taught by faculty like Mark Caddick.
Over 70 alumni.
There's a quote from student Angelina Stevens. She talks about seeing high alpine peaks and exhumed mantle rocks in person, calling it a once-in-a-lifetime cultural and scientific experience.
It permanently alters how they understand the Earth. And the newsletter is very transparent about this. There's a stark financial reality underlying all of this.
The graduate funding gap.
It's a massive hurdle. Grad students run the labs. During the year they teach, but the summer.
It costs about $10,000 to fund a grad student over the summer so they can actually do their thesis research.
Yeah, and the department faces a $50,000 structural shortfall every year,
Forcing these brilliant scientists into side jobs just to pay rent.
which delays the world-changing research we just talked about.
But the Geosciences Advisory Board, led by David Spears, stepped up.
They ran a targeted Giving Day challenge.
And the results were immediate. They funded Esther Oidel.
Who researches groundwater with NCRR in Boulder.
Because she was funded, she didn't need a side job. Her research accelerated, and she ended up presenting at UN COP30 in Brazil.
Incredible ROI. And it also funded Alex Ellers.
Working on high entropy materials, she literally said the scholarship saved her defense timeline from being delayed a whole semester.
Financial runways are just as important as intellectual brilliance.
They really are. And that focus on the people leads us to the final theme today: legacy and passing the torch.
Geology is the study of deep time, but a university department runs on human time.
We have new leadership. Jim Spatilla is taking over as head from Steve Holbrook.
Holbrook had a massive 8-year run, doubled undergrad enrollment, grew the faculty by 25%, and got them through COVID.
And Spatilla is focusing on grand challenges: water, energy, hazards, calling on alumni to mentor the new workforce.
But they also took time to remember the giants on whose shoulders they stand. The in memoriam section.
3 foundational professors. First, Dr. Richard Bamback.
A revered paleontologist.
The anecdotes about him were just beautiful, holding a can of Coke, laughing off a student's crisis, his incredible optimism. When a student was stressed about a tough job market, he just said they needed to hire someone.
And his legacy lives on in the BK Meals tradition.
Even though the Burger King is gone. Then there was Dr. Jerry Gibbs, passed away at 96.
A World War II Navy vet. Used the GI Bill.
He published a seminal 1982 paper on quantum chemistry in silicates, won the Roebling Medal.
And the Irish proverb from his memorial is so profound. Don't think that he is gone, but that he was here.
It's perfect. Finally, Dr. Fred Reed.
The classic field geologist. Ran the CRAP Group Carbonate Research Appalachian Arctic Project.
Best acronym ever. He was remembered for pushing his students incredibly hard in the field, demanding their absolute best.
And then being the first one to relax with a cold beer with them at the end of the day.
It's just a reminder that science is a deeply human endeavor.
Driven by mentorship, humor, and multi-generational passion.
It really is. So just synthesizing all of this, the sheer scale of what we've unpacked today is wild.
That's a massive spectrum.
We started with a microscopic speck of Ehrigite in Canada and a new metal-rich mineral in China. We zoomed out to billion-ton carbon capture projects, deep time extinction modeling, and searching for life on Mars. And we ended with the personal legacies of the humans driving it all.
It's breathtaking. And to leave you, the listener, with a final thought to mull over, think back to geometallurgy.
That the machine learning.
Right. Scientists using AI to look at submicroscopic specks of tellurium to predict the massive behavior of a mining plant years before it's built.
Yeah.
Now apply that to us. With scientists analyzing deep time extinction data and extreme limits of life, are we as a society learning to apply a geometallurgical predictive model to humanity itself?
Oh, wow.
If we can forecast the behavior of ore based on a 100-micron crystal, can we use the geologic record to accurately forecast and course-correct the survival of our own species?
If we can read the rocks that closely, can we rewrite our own future? That is a profound question to end on. Thank you for joining us on this deep dive from the microscopic to the monumental. Keep your curiosity ignited, and we will catch you next time.